Hello, my name is Chris Evans, and I'm from Physical Sciences Incorporated. This talk is entitled A Wavelength Scalable Dual-Stage Photonic Integrated Circuit Spectrometer and is funded by ONR. Physical Sciences Incorporated, or PSI, is a 50-plus-year-old company with over 275 employees. We are an applied R&D company that focuses on technology transition across a wide range of disciplines for both our government and industrial customers. Our expertise includes underwater sensors, integrated photonics, and optical communications. We have developed products for a variety of applications, including ISR systems, laser-based sensors such as the handheld methane sensor shown on the right, radiation sensors mounted on highway gantries, as shown on the bottom left, that monitor the transport of radioactive materials, RF and optical components, as well as tactical systems including ruggedized drones, as shown on the lower right. For every dollar of Phase 2 SBIR investment, PSI has secured nearly 3 times that amount in Phase 3 funding. ONR is developing on-chip Raman sensors that leverage photonic integrated circuits to enhance chemical detection. Normally, a Raman microscope uses a high numerical aperture objective lens to focus laser light onto the sample of interest, which subsequently generates the Raman signal or Stokes signal through inelastic scattering. The frequency shifted spectrum of the Stokes signal is measured using a spectrometer, which allows us to identify which chemical is present. For Raman microscopy, the signal is predominantly generated at the focal point, which quickly diverges, limiting the total amount of signal. To overcome this divergence, we can use the evanescent field just outside of a thin submicron waveguide. Here, we place a liquid directly on top of the waveguide or add a chemical coating that concentrates the analyte near the surface of the waveguide. As we launch the pump laser's light into the waveguide, the analyte inelastically scatters the pump photons to generate the Stokes light, which is also guided in the waveguide along with the pump. As both the laser's light and the Stokes signal do not diverge, we can significantly increase the signal simply by increasing the waveguide's path length. While these sensors can be created using compact and mass-producible photonic chips, these still require a spectrometer to form the full sensor. Therefore, to realize a low-swap, fully integrated system, we need to design and integrate the spectrometer on the same chip. Creating a photonic integrated circuit spectrometer is a challenge, specifically because it requires simultaneously achieving high resolutions over very wide bandwidths. In addition, it requires high channel-to-channel extinction ratios, and ideally, it is a direct readout technique that doesn't require post-processing. Here, we compare several different types of photonic integrated circuit spectrometers and compare them based on their bandwidth, resolution, extinction ratio, and readout methods. What we see is that no single spectrometer type is capable of simultaneously achieving high resolution over wide bandwidths. We see that arrayed waveguide gratings are able to achieve very wide bandwidths, however the resolution suffers. Meanwhile, microresonator-based spectrometers can achieve very high resolutions, yet their bandwidths are very small. Our approach is to cascade these two spectrometer types to create an aggregate spectrometer that can achieve both the resolution and bandwidth requirements for Raman spectroscopy. Our dual-stage photonic integrated circuit spectrometer cascades these two spectrometer types, an AWG and a series of microresonators, to create an aggregate spectrometer that can achieve both high resolution over wide bandwidths, as shown below. Here, light enters into the chip and goes to the AWG, which divides the light into several coarse channels, roughly every 5 nanometers. The coarse channels then go to a series of high-resolution add-drop microresonators we refer to as the high-resolution banks. Each bank contains a bus waveguide with a series of progressively larger microresonators, where each resonator removes a different wavelength range from the bus waveguide using their respective drop ports. The outputs from these resonators are sent to a detector array, completing the spectrometer. While this program is targeting an off-chip detector array, on-chip detectors are readily available from many foundry services. This program leverages silicon nitride to realize a novel cascaded spectrometer design that can be transitioned to a commercial foundry's process design kit for incorporation into new chip designs. Silicon nitride is a key material platform that provides wide transparency from visible to near-infrared wavelengths with very low propagation losses. In addition, silicon nitride is highly mass-producible using CMOS fabrication techniques. Our cascaded spectrometer design uses arrayed waveguide gratings with special multi-ring microresonators known as coupled resonator optical waveguides, or CROs. The AWGs provide access to wider bandwidths, while the CROs allow us to achieve higher resolution. In addition, by adjusting the physical parameters of the CROs, we can tune the flatness and extinction ratios of their filter functions to optimize their performance for different applications. Lastly, the resulting designs can be included as a building block component within a commercial foundry's process design kit, or PDK. This approach will enable PSI spectrometer to be licensed and incorporated into new chip designs for external users. We have conducted 2 rounds of fabrication with AIM Photonics. The resulting chips have achieved a bandwidth of 125 nanometers with a resolution of 0.5 nanometers across 250 channels. These specifications are well aligned to Raman spectroscopy using a 780 nanometer pump. This program is currently within the Phase 2 option period of performance, where we are targeting a waveguide enhanced Raman demonstration in addition to developing our building block component. Our photonic integrated circuit spectrometer has several key features. First, its high resolution meets or exceeds the requirements for Raman spectroscopy, making it well matched for future ultra-portable Raman spectrometers. Furthermore, by increasing the resolution of these spectrometers, we can resolve subtle shifts in the frequency of the Raman spectrum that cannot be resolved by typical Raman spectrometers, thus providing an advanced analysis tool in the field. Its wide bandwidth currently spans the entire molecular fingerprinting window to enable molecular identification. This bandwidth can be further extended to beyond 3,000 wave numbers to realize a compact Raman spectrometer with the full capabilities of a benchtop analytical tool. Our spectrometer targets a 780 nanometer pump, which balances Raman signal generation with reduced background fluorescence to improve signal-to-noise levels for detecting trace molecules. In addition, all relevant wavelengths are compatible with high-performance, low-cost silicon detectors. By leveraging wafer-scale lithographic fabrication methods, we can increase the on-chip component density to realize higher resolutions and wider bandwidths. In addition, wafer-scale fabrication provides a way to mass-produce chips, greatly reducing the cost at scale to enable wide deployment. Finally, our designs can be adapted to different wavelength ranges to accommodate different pump wavelengths, bandwidths, and resolutions for a variety of applications beyond Raman spectroscopy. To transition this technology, we recognize that a chip-based spectrometer is a key component for many advanced sensor platforms. While our current focus is to demonstrate a spectrometer compatible with waveguide-enhanced Raman spectroscopy, by creating a building block component for a commercial foundry, we will provide other design engineers a drag-and-drop solution to easily incorporate our spectrometers into future photonic chips targeting different applications. While we are aware of several other applications, we want to know, how could a low-swap spectrometer enable your application? To commercialize this technology, we are first developing spectrometer building block components for several wavelength ranges and resolutions. These validated designs will be licensable through a commercial foundry for ready incorporation into a range of new chips. In addition, we are looking to create fully packaged device variants that use this technology, including low-swap spectrometer units as well as portable waveguide-enhanced Raman spectrometers that integrate a laser, Raman sensing section, and our spectrometer into a compact, ultra-portable package. In addition to ONR, we anticipate other end users that may include law enforcement, for example, to provide police officers with the ability to identify a wide range of unknown substances on the scene, as well as for healthcare and diagnostics, where the low cost and high manufacturability of our technology may enable portable or even at-home health monitoring applications. In summary, PSI is developing very low-swap chip-based spectrometers that can achieve wide bandwidths and appropriate resolutions for Raman spectroscopy. Using chip-based technology, we can directly interface with advanced waveguide enhanced sensors. Our design is easily adaptable to wider bandwidths, higher resolutions, or both simultaneously. PSI's goal within this program is to realize a photonic building block component for easy incorporation into new photonic chips. Come chat with us and explore how PIC-based spectrometers can enable your application.